Hey there, physics students. In this video, we're going to have a very general discussion of concepts of torque, equilibrium, and a little bit of center of mass. Now, in order to help us in our discussion, I'm going to use something called a balance bar, or you might refer to it as a seesaw. Either way is fine. This balance bar is made of a meter stick, which is good for two reasons. One, it has markings on it that we can easily determine measurements along the balance bar's distance. And it is also a uniform mass, which means the mass is evenly distributed throughout the material, and so that the center of mass is really darn close to the geometric center of the meter stick. Now, it may not be exactly at the 50 centimeter mark, because as you know, students use these in class, they might hit them on the table, and over years, the ends might get worn away, and so may shift the center a little bit off from the 50. I found the center of mass by dragging my fingers together, put the clamp on. The clamp has a little fulcrum, and it fits in this little perch. And so sure enough, I did a good job, if I do say so myself, of finding the center of mass because, of course, it's balanced. Now, what does balanced really mean? Well, we've heard about balanced forces. We also have balanced torques now. So we would say that this object is balanced because it has no net force and no net torque. And when that condition exists, we have a system that is in equilibrium. Now, equilibrium, as I said, means no net force. It means up forces equal down forces, left forces equal right forces, and clockwise rotation equals counterclockwise torques. Sorry, I said rotation, but torques equal torques, okay? Now, you might say, well, wait a second. There are forces acting on this. Yes, there are, but no net force, right? So the force that's acting on, the primary force, is the gravitational force, the weight force pulling the meter stick down towards the center of the earth. There's a counterbalancing normal force from the perch that pushes up on the fulcrum to hold the meter stick from falling, okay? Now, because the fulcrum allows it to move, we have what's called an axis of rotation here, okay? Remember, the axis is perpendicular to the plane of rotation. Now, the axis of rotation is at the center of mass. Because of that, there is no net torque on this object either, because the center of mass is where all of the weight force is concentrated, because all objects, regardless of mass, regardless of shape, act as if all of their mass is concentrated at the center of mass. And as we said before, it happens to be in the geometric center of this as well. Now, why does this cause no torque? Because torque, if you remember, is equal to force times lever arm, okay? Force times lever arm. And the lever arm, we remember, is the distance between the axis and where the forces are applied. And because the force is applied at the axis, there is no torque that is applied by the weight force of the meter stick, or the normal force for that matter. Now, that can change if we reposition things, and we'll play with that a little bit as we go along. Now, we can change this equilibrium system, okay, this system from equilibrium, I'm going to just put some brackets on here real quickly, and you can see clearly there's a net torque now, because now the meter stick falls right off, okay, even knocks it out of the perch, okay. We'll put a second bracket on here. Now, we actually could probably balance this thing with just the brackets, but we want to be a little more quantitative than that. Not too quantitative, but a little quantitative. We'll go ahead and put a 200-gram mass on here. That means there's about a 2-Newton force over there. And we'll put a 200-gram mass over here, and that means there's about a 2-Newton force over there. Now, surely you can see that we have a 2-Newton force here on the right side, or the left side, pardon me, and a 2-Newton force on the right side, okay? And when you might say that now we have forces, okay? Those forces have to be balanced because we've got a 2-Newton force over here, 2-Newton force over here, and so those forces must balance out the rotation. But no, they don't, okay? Because forces don't cause rotation, torque causes rotation, and torque is force times lever arm. Now, if the forces are the same, which they are, okay, then the torques must be different, so that means the lever arm must be different. And I think you can see that even though it's close, that these two distances are a little bit, they're not the same, okay? So what I'm going to do is I'm just going to go ahead and slide the other one inward to make that lever arm a little bit closer, and maybe I'll slide that in a little more and get it from not swinging, so this can be a little more gentle. And I'm going to go ahead, and that one's still not quite there. And so this is a process and something that even a grade schooler could understand. Finding the equilibrium point, finding the balance point is not that hard of a concept, but we want to make sure that we understand what it means quantitatively and how we can define torque and equilibrium in these systems. So I'm going to get this as close as I possibly can and then continue talking. Okay, so I just did that kind of by feel and by eye. Now I can't see the measurements on the front side. The back side doesn't have useful measurements for me. So I don't know what the lever arms are, but I bet they're pretty darn close. And so what I'll use is I'll use a tape measure just so we have something that is of a uniform distance. And I'll just go from the axis. So you can see from the whole tape measure, the back of the tape measure to the axis is about that far. I'm not even concerned with what the numbers are. But if you look, if I move it over to here, and they're exactly the same. Okay, so that checks out, no problem. Interestingly, you might say, well, what about forces? Are the forces still balanced? Well, sure they are, because now we have the weight of the meter stick down, the 2 Newton force over here, the 2 Newton force down. So now we have the weight of the meter stick up, whatever magnitude that is, and 4 Newtons of force upward. It has to be, because the meter stick's not jumping up off the table and it's not falling to the center of the earth. Okay, so let's go ahead and do something, again, a little more quantitative. So let me just make sure these are snug so they don't fly off. And when I take the 200-gram mass off this side, you can see that now there's a net torque over here, and so the meter stick falls down. I'm going to go ahead and put a 100-gram mass on there, and sure enough, as you would expect, it doesn't fall, it doesn't go down, it doesn't balance out, because of course it's not force that causes, not just force that causes the rotation, it's torque. Okay, so we have the lever arms are the same, but now the forces are different. So we have a greater torque over here and a lesser torque over here. We can change that by doing one of two things. One, we could just add the force back to it with another 100-gram mass, and you can see we've got another balanced situation. Or take that 100-gram mass off, so now we got 100 grams, so 1 Newton, 2 Newtons, and we can change the positions of these masses, the lever arm, and put it back into balance. Now, how did I know to move the 200-gram? Well, I didn't, but you could move either one. I would have to move the 200-gram smaller, right? Because if F is big, L's got to be small. Then I just can see I can't move the 100-gram off the end of the meter stick. Okay, so I'm just going to do this. Again, this is like, grade school, 8th grade science, maybe 3rd grade science, I don't know. And there we go. Okay, so now I'll bet you, whatever you want, that this distance is approximately half of this distance. And I'll just use my rudimentary finger measurements, and sure enough, it looks like that's about the case. So a balance bar or a seesaw is really useful to understanding torque, rotation, equilibrium, and the like. I want to focus in on center of mass one more time for one last little demonstration. So what I'm going to do is I'm going to take these brackets off, and I'm going to mark the center of mass, actually, so that I know where it is. And we're going to make sure that we keep track of that. It's about at 50.3 centimeters. So we'll go ahead and take that off, and I'll put a marker on there. And I'm going to take this fulcrum, and I'm going to move the fulcrum over to one end of the meter stick, probably around the 80 centimeter mark or so. It doesn't need to be exact, but clearly this is not a balanced system anymore. This is not a system that is in equilibrium, if you will. Okay, even if I put just the bracket on, the meter stick is just way too heavy. Now, why is that? Let's just take the brackets off for a minute. Why is this happening? What is going on here? Why does this fall? Well, the reason it falls is because, let's not forget, all of the mass of the meter stick acts as if it is concentrated at the center of mass, which we said was right about here. Okay? And when we go ahead and think about that, that means there's a net torque from the center of mass on this side of this axis of rotation. Okay? So our fulcrum's here, and we're going to continue to use our axis of rotation over here. Now, when we do this, we can get this to balance, and if we put a bracket on here, And we put our, let's say our 200 gram mass on here. And oh, that's too much. Okay, so let's try a bracket over here. And we'll go ahead and put a bracket on here and see if we can balance it. Well, now that's too much. So what I'm going to do is I'm going to go ahead and add a second 200 gram over here. So I've increased my torque. And I'm going to see if I can balance this meter stick by putting a little bit more mass on here. I'll put a really small mass. This is about 20 grams. And when I do, what you'll notice is when this gets balanced, I think you can tell F times L, or force times lever arm, it doesn't really matter how big or small the meter stick is. You're going to be able to find a balance point based on the concept of balanced torques. Okay. Now you might say that the torques involved here are the force over here times this lever arm, plus, and then the force over here times this lever arm. But that's not all that's happening, because remember, the center of mass of the meter stick is also pulling down in this direction towards the center of the earth, as if all of the mass of the meter stick was concentrated right here. Now, why didn't we worry about the center of mass causing a torque before? Because before, the center of mass was where the fulcrum was, okay? And when the center of mass is where the fulcrum is, like in this one, there is no net torque from the center of mass. However, when the fulcrum and the center of mass are not in the same place, we have a net torque that is provided by the meter stick. And if you don't believe me, take all the masses off, and you know what's going to happen. The meter stick falls because there's a net torque downward. Okay, that's about it. Real brief and general discussion of torque, rotational equilibrium, and center of mass. See you next time.